So if I ask you to evaluate this definite integral, you know to evaluate definite integrals, when we first introduced something like this, it was with like finding displacement or distance. And we could do velocity times time, area under a velocity curve, or we know we could find the change in position. Okay, so this is what I want us to go back to whenever I say like why. Why would you take the antiderivative? The whole ending position minus starting position, the whole area under a derivative gives us a displacement of its original function. Okay, now we weren't able to do this maybe at the first lesson of this unit because we didn't know U substitution. Now that we know U substitution, we now can take this antiderivative and go from there. Okay, so we see U would be equal to the inside of the composition. Du would be 2x dx. I like to write it as dx on the right side equals 1 over 2x du on the left side, but to each their own. And now, I'm going to write an integral, but I'm not going to put any numbers down. Please don't put any numbers down yet. And we're going to just fill in the U substitution step. I got x root u. I have 1 over 2x du. Okay, and the x's cancel like they normally do. All right, typically, when we're like, before we've taken the antiderivative, we would place these numbers 0 and 2 right here. But this is wrong. Why that's wrong is interesting. Okay? Well, we are trying to take an antiderivative with respect to x, or we're doing an infinite sum of heights times widths, the widths being dx. Remember what dx stands for besides with respect to x? Does anybody remember another meaning besides with respect to x? dy dx. Why did we have dy dx? Dy dx we didn't say was with respect to y over with respect to x. Close. That's the fact that this is like a d, almost like a Greek symbol delta. What does the delta x stand for? An overall change. Dx would be a infinitely small change in x. All right, infinitely small change in x. Okay? It's just a very, very skinny width of a rectangle, right? Remember we could say these are heights and then this is widths. If we're doing like a right Riemann sum idea of things, that will help us when we get into next unit. Okay, but here's the thing. dx, x's, change in x's. These, 0 and 2, these are x's. But once I change things to du, all of a sudden I have an infinitely small change in u, which means I can't use x's anymore. We're no longer on an x-axis. I'm on a u-axis. Okay? So I need u's. All right, what are the numbers that go there? See if you and your neighbors can figure it out. Very, very good. 2 and 6. Almost all of you got that. It's not not usually the case for classes. So good job. You guys are paying attention after lunch. This is great. This is the connection between x's and u's. You establish the connection when you set u equal to something. Well, that means if x is 0, u is going to be 0 squared plus 2. That's 2. If x is 2, this is 2 squared, which is 4 plus 2, which is 6. Okay, great. So what we've just done, this process, is called changing bases. Change of bases, changing bases. I'll call that change of bases. Okay, so we changed our bases, 0 to 2, x-axis, base of rectangles, to 2 to 6, u-axis, changing u's. All right, so now I got 2 to 6. I'll rewrite this so it's nice. U to the 1/2. Let's go ahead and do the next step. What would be the next step? What's the next step? Take the antiderivative, okay? We don't forget this step. This is the most important step. Take the antiderivative. So I get u to the 3/2, and then 2/3, so that becomes 1/3. U to the 3/2 plus a c. Do I need this plus c? I don't, because I'm finding the change in this between 2 and 6. Right, my new bases. But what's usually the last step when you're going through and taking the antiderivative using U substitution? Like on your quiz today, what was the last step that you did for every single one of the antiderivatives on the back? Right, plug in x squared plus 2 back in for u. Well, we could do that. I'm going to put an or. It's an or 1/3 x squared plus 2 to the 3/2 plus c. I don't need the c. On this line, am I going to put 2 and 6? Like I did up here, 2 and 6? Back to 0 and 2 because we have x's. Now what we find is regardless of which one we do, whether we are plugging in 6 into u and 2 into u, or 2 into x squared plus 2 and 0 into x squared plus 2, we are going to get the same answer. It's not nice, you can't simplify it, but whatever. 1/3 6 to the 3/2 minus 1/3 2 to the 3/2. Okay, if you look right here, plug in 2, that turned into 6 to the 3/2, 1/3 6 to the 3/2, 1/3 2 to the 3/2, so we end up with the same answer. Let me just move this stuff forward a bit. All right, cool. Well, one of you is probably thinking something right now, and you probably have a question. Anybody have a question? I mean, it just happens to work so that they end up being the same thing. The 6 to the 3/2 times 1/3 minus the 2 to the 3/2 times 1/3. Okay, the x's is 2 squared plus, yep, ends up being the same thing. Do you find anything, put your phone away. Do you find anything unnecessary? 1/3 is very necessary. What I'm trying to allude to, and it's okay, it's like, why bother changing 0 to 2 to 2 to 6 if I can just go back to 0 to 2? It's like, oh, I went from 0 to 2, I changed it to 2 to 6. Okay, I could plug in 6 and 2 in here, but if I'm just comfortable always doing that last step of plugging in the x's, and I just go back to 0 and 2, why bother, right? Why bother? And really is the question is, which one would we prefer? Do we prefer to plug in 0 and 2 here at the first step? Or could we have just ignored that and then we plug 0, 2 in here at the last step and we get the same answer? Okay, so it's like, is change of bases necessary? Turns out, no, it's not necessary. So if I gave you this problem here, it's going to be a long, messy answer. But if I asked you to find the area from 0 to 2 of this, okay, well, let's see. U equals x cubed plus 1. Du is equal to 3x squared dx. dx is 1 over 3x squared du. I got an integral 2x squared u to the 4th 1 over 3x squared du. Cancel, cancel. I got 2/3 u to the 4th du. I take the antiderivative. Becomes u to the 5th times 1/5. That's 2/15 u to the 5th plus c. Might as well change it back into 2/15 x cubed plus 1 to the 5th plus c. But don't need the c because I can just plug in 2 and 0. This is 2/15 9 to the 15th minus 2/15 1, not the 15th to the 5th. To the 5th is just 1. Right? Doesn't this look nice? Don't have to bother with anything that's crazy. So know that you could just do that. Okay? You could do that. However, there will be questions, and the next question we're going to do, that will require you to understand this process of changing our bases. Okay? So I would like you, and I say it in the homework, to show all the steps of changing your bases because of the questions in which they're necessary. So 0, 2 turns into 9 and 1 when I change from an x-axis to a u-axis. This would be 1, this is 9. This, from 1 to 9, would give us the same as this from 0 to 2. Yeah.
So when is it necessary to do it?
For this problem, flip the page, go to this problem. Here's the problem. Here's your answer and what it's going to look like. I'd like you to find the number that goes here, here, and here. Okay? So it says you have an integral like this. Rewrite it like an integral like this. You'll see a lot of your homework problems are like this. This requires you to understand the change of bases. Okay? Let's see if you can do it. Good. I like what I'm seeing from a lot of you. I'm liking what I'm seeing from pretty much all of you, which is the u equals 2x, the connection between u's and x's, and then the understanding that if these are x's, our u's would have to be double that, 8 and 18. Good. If you just stop there, you're not going to get the right answer. And if you just say, oh, 8, 18, I guess I have a 6 over here, this actually is incorrect. Okay? And we know that is not what we do when we do U substitution. We don't just say U equals something and that's all we do. We do a lot of stuff after we identify what U is equal to. So start doing all the other steps of U substitution if you haven't started already. So you got du equals 2 dx. Okay, good. We got dx equals 1/2 du. Okay, good. We then rewrite your integral. Okay, I know I got 8 and 18. That's good because I'm changing things to du. But all of a sudden, if I've done things correctly, I have this. Now, I don't want to take the antiderivative of this. I want my answer to be in the form of an integral. So my answer that they want us to provide does not have a 1/2 in it. Okay, so what do? Discuss with your neighbors. You got to remember your integral properties. Yeah, if we remember, there's an integral property that states that you can take this 1/2, this constant, this product, and if it's 1/2 times, you could pull that 1/2 out. You don't really have to, but maybe it's easier to see that, oh, I'd have to multiply everything by 2. And when I multiply everything by 2, I realize that this number is 12. Okay? Here's a good one where like changing bases is not a big deal. You're told that u is equal to root x. We understand this is 2 and 1. But watch what happens. If u is root x, du is 1/2 x to the negative 1/2 dx. dx would equal, ends up being root x over 2. Nope, 2 root x. This is 2 root x du. Okay, I rewrote this as 1 over 2 root x dx. Multiplied, I got that. Okay, cool. So 1 to 2, that's easy. When I do the U substitution step, I have e to the u, and then, okay, root x, that's u, and then I have 2 root x du. I think you might have seen one of these on your homeworks that we're due today. Typically, x's cancel, right? I have x's and u's, and it doesn't look like I can cancel. Anybody see the key? Since root x equals u, these are the same. And I didn't have to change that root x on the bottom to u. So maybe you have the 2 on the outside, e to the u. That'd be the equivalent one. You could actually evaluate this too. 2 e to the u is the antiderivative plus c from 1 to 2 should be 2e squared minus 2e. Okay. Again, yeah, you actually didn't have to change your bases there, but you are required to know how to change your bases, which is why I'd like you to do all the change of basis steps for every problem that you do in your homework problems. Okay, so that kind of covers U substitution. We're almost actually all the way covered with U substitution. And most of the U substitution things that we've done have dealt with products. So x times root x squared. 2x squared times x cubed plus 1 to the 4th. Well, we're going to change it up and talk about quotients. Okay? And there's 4 situations with quotients that we need to be prepared to handle when taking antiderivatives. Okay? Let's look at this first one. Tell your neighbor, what do you do to take the antiderivative of this first one? I mean, I gave you the hint. Simplify. But how do you simplify? Yeah, this is a common denominator. I have multiple terms divided by one term. If I'm dividing by one term, I can split this up. And we'll talk about how sometimes if you have one term over multiple terms, you can't simplify like that. Okay, split it into multiple terms, antiderivative of each. Okay, good with that. Remember, negative first power, we have a log as the antiderivative. Second situation, f of ax plus b. The one on the right. We know it's x to the negative first, or it's this kind of quantity to the negative first power. If we moved it up, well, we know that the natural log function handles that x to the negative first. But we also remember we need the reciprocal of the coefficient of x. So this is like on your quiz today. I put the one on the left in because I want us to remember you don't use logs for anything in a denominator. This I would rewrite as 2x plus 3 to the negative second. And you actually could use U substitution to do this, but man, is it a lot more efficient if you just do the antiderivative of the outside, leave the inside alone, and then you multiply by the reciprocal of the coefficient, giving you a negative 1 over 2x plus 3 plus c. A lot more efficient doing that. Okay, so let's all review. First situation, second situation. The third situation, not reviewed. And I want us to change this from u and u prime to f and f prime. Okay. Here, we are dividing 3x by x squared plus 5. First thing to identify is that you can't simplify. You are not allowed to split this into 3x over x squared plus 3x over 5. We know that that's not true, because the only way you could add fractions is having common denominators. So this is wrong. It is very tough to split up fractions like this easily. There are methods to split up fractions, but this is not how you do it. So is everybody comfortable with saying, no, I can't simplify like that? Good. All right. I notice that the numerator is a version of the derivative of the denominator. I have f prime divided by f. Here's what we're going to do. We're going to set u equal to the denominator. I'll do it on the left side. You don't have to copy down, but copy down the one on the right side. U equal to the denominator. All right, so du will equal f prime of x dx. Here you'll have du is equal to 2x dx. We do the same thing. We solve for dx, wherever your dx may end up. So you guys solve for dx. We will substitute like normal. This is just regular U substitution. So I got f prime of x. This is u. This is 1 over f prime of x du. Over here, this turns into 3x over u and 1 over 2x du. If stuff is correct in the world, you'll be able to get rid of the x's. And you will just leave essentially 1 over u, but you may have some constants. Here, I'm able to get rid of these x's, and I leave what probably you would write down as 3 over 2u. Now, the one on the left, we remember, and this is a good one to remind us, that the antiderivative of 1 over u is log absolute u plus c. So I'd end up with log absolute f of x plus c. The one on the right side is not as obvious because of the constants and the fact that you have a constant times u. Now, you could do things like we've done them before and say, okay, 3 log 2u times a half, and then add a c. Or you can easily split this fraction up, since it's all multiplication, into 3/2 times 1 over u. And since this constant can be pulled out, you can just have 3/2 log absolute u. You might be thinking, these do not look the same. And if you plugged in what u is equal to, you wouldn't get the same thing. But what I'm telling you is they're both the correct answers. I would probably prefer you to use this technique moving forward. If there's no addition in the denominator, you can just pull out the constant and do that. It makes for an easier answer, though if you did it the other way, it's still a correct answer. Okay, like you could test both of these, take the derivatives of it, you'd get the same thing. Okay? All right, your turn. Go ahead and take the antiderivative of this, and then I'll show you the antiderivative of tangent, which actually we haven't been able to do, and we don't know, and we'll find out shortly. So do the one on the top left, antiderivative of x squared over 3x cubed plus 2. First thing I notice is I can't simplify. Okay, so I can't simplify. I notice that the numerator is a version of the denominator. The denominator's derivative. So I see kind of like an f prime over f situation. I'll set u equal to the denominator. Okay. Here the composition is the fact that it's like a denominator to the first power. It's not obvious. It's not seen as obvious, but maybe that's what it is right there. So all the other U substitutions where we set U equal to the inside of a composition, it's easy to identify. You're going to have to be able to identify this on your own moving forward. Oops, that's U. I would not combine things. I'd probably leave it separate, 1/9, 1 over u. That way my antiderivative is simply 1/9 log absolute u, which is 1/9 log 3x cubed plus 2 plus c. And just so you know, you could have, numbers, from 0 to 1. 0 to 1 would change to 2 to 5. 2 to 5. Either find the change in this between 5 and 2, or find the change in this between 0 and 1. You get the same answers. You'll have some homework questions where you need to remember that the log of 1 is 0. You need to remember that the log of e is 1. Remember the log of e to any power is the power. So just remember that, because it's expected of you to know, and you would never see an answer on a multiple choice question. You'll have some multiple choice in your test coming up where it has log of 1. You're expected to know the log of 1 is 0. All right, let's get to tangent. We actually can now take the antiderivative of tangent. We don't know what it is. Ready? I'll walk you through it. First, I'd rewrite this as sine over cosine. I see that the numerator is a version of the derivative of my denominator. I'll set u equal to the denominator. I remember the correct order for derivatives, so cosine's derivative is negative sine. I'm going to solve for dx. And I get sine x over u times negative 1 over sine x du. The sine x's will cancel. I have negative 1 over u. The antiderivative would be log absolute u plus c. The antiderivative of tangent ends up being log absolute cos x plus c, and that needs to be a negative because that's negative. Isn't that complicated? A lot more complicated than you probably thought it would be, but that's what it is. Good, but let's get to some trickier ones that you guys are going to be excited to do. Let's go to the fourth situation. The numerator is a greater power than the denominator, and the denominator doesn't just have one term, it's got multiple terms. You might think u equals the numerator. It's not going to cancel. It's not going to help us. You ready? Can't factor the numerator. We need to remember long division or synthetic division of polynomials. We need to simplify this by dividing. So I need to take x minus 1 and divide it into x squared plus 2x plus 3. You could do this if it's just x minus a number or x plus a number using synthetic division. Synthetic division is very easy if you remember how to do it. You will place the root. The reason why they place the root is so that we end up adding, versus here the situation is we'll subtract. And then we'll place the coefficients. We like to place a line down here. Okay? I'll walk you through the long division, and then I'll show you where the numbers come from in the synthetic division. Okay? First thing is we try to figure out what the largest value is to be multiplied by this to start canceling some terms. So I want to get rid of x squared. X times x minus 1 will give me x squared. So I multiply x by x minus 1. It's the whole how to divide, a big number by a number. We try to get rid of each thing as much as we can. So we'd say okay, 7 times 4 is 28. Subtract, right? And then you bring down a 5 and then a 0. Okay, 7 times 7, 49, and then you subtract. Do we remember this? If we don't remember this, then that's a problem. But who knows what's taught in elementary schools these days. I end up with a remainder in this situation. That means 3,006 divided by 7 is 472 and 2 sevenths. Okay? That remainder is like a decimal. We cool with that? And we'd get the decimal answer. I don't have enough time to do that, and I know 2 sevenths is not going to be a nice decimal, so I'm going to just stop right there. Okay? All right, so we pick x so we can get rid of the x squared. You multiply x by x minus 1, you get x squared minus x. We then subtract, just like I subtracted here. Now I'm subtracting this quantity, which means we need to subtract this. Okay, that's 0, but when I subtract the negative x, that's like adding a positive x. I'd recommend that if you are using long division that you change things to add the opposite. All right, so now, where do these numbers come from? Watch this. If you bring down this 1 ends up corresponding with this x. Then you multiply these two numbers together, you put it there. Well, 1 times 1, that's how we get this positive 1x. And then 2 plus 1, that's how we get this 3. That's where we're going to get this 3 from. So we like bring down, we multiply diagonally, and then we add going down. Now, same process, I could bring down the 3. What would get rid of the 3x plus 3 is if I had a positive 3. 3 times x minus 1 is 3x minus 3. But again, I'm going to be subtracting this. When I subtract this, it's the same as adding the opposite. So if I add the opposite, this ends up with a value of 6. There's nothing else to bring down. This is my remainder. Well, 1 times 3 gives me 3. That's where this 3 comes from. 3 plus 3 gives me 6. Here's my remainder 6 using synthetic division. Now, what does this mean? This integral can be written as x plus 3 plus 6 x minus first. You can see what it is here with the remainder. Here, this is my remainder. These, next to my remainder is always my numbers. These are always my x's, and so on and so forth. Then x squareds, so on and so forth. So we've done all that work just so that we can now take the antiderivative. The antiderivative of x, I can do that, 1/2 x squared. The antiderivative of 3, I can do that, 3x. Antiderivative of 6 over x minus 1, 6 log absolute x minus 1. Okay, I'm going to do the other example right now. If you'd like another example of long division. Easiest thing with longer ones is to definitely use synthetic. I'll show you how quick it is with synthetic, but let's just go through both of them. Okay. All right, so I'm long dividing, or I'm synthetic dividing. I would have x squared. That's where this 1 comes from. Multiply, I get x cubed plus 2x squared. Subtract. I multiply this negative. That gives me a negative 2. Add. I get to negative 5. Opposite, negative 5x squared. Bring down the 8x. Here, kind of the 8 is brought down. Negative 2 times negative 5, positive 10. Add to get negative 2. Watch positive 2. Watch how that pops up over here. I'd have a negative 5. There you go. There's that negative 5, because the negative 5 times x plus 2 gives me negative 5. I need an x, negative 5x squared. Negative 5 times positive 2 is negative 10x. Subtract. Same as adding the opposite. And if I add these two numbers, there's that 10, there's that 10. Add the two numbers, I get 2. Bring down the 5. I'll see that I need a 2 here. That's where this 2 comes from. And then I'll end up with a remainder of 1. I'll see that 1 pop up here at the end after I multiply. 2 times x plus 2 is 2x plus 4. Subtract. There's my 1 remainder. Okay, so that'd be this plus 1 over x plus 2. I can see there's my number, these are my x's, these are my x squareds. The antiderivative of this can be written as the antiderivative of x squared minus 5x plus 2 plus 1, x plus 2th. And the antiderivative would be 1/3 x cubed minus 5/2 x squared plus 2x plus log absolute x plus 2 plus c. Okay, pretty intense, but that is long division with polynomials. Numerator greater than denominator. So that's part of your expectations. You'll see those on your homework. Thank you.